Well, hello. Today I felt like we are going to lift some myth about the BJT transistor. And as you know, perhaps the transistor has the symbol here and here the base. So we have on the transistor the collector, the base, and the emitter. And we can connect something up to the emitter, something up to the collector, and something up to the base. So that's a common scenario. And I tell you the one that I use. Oftentimes it's this one, the BC547C. And it said sometimes on the internet that it's the European equivalent of the 2N2222. That is not quite true because these ones I read up and they are rated for 100 milliamps, and the 2N222 it can endure up to an amp or so. So it's a good alternative, but they are not the same, not at all. So that's the practical thing. So that's the theoretical symbol here. And the thing is that it very much depends what you connect up to this transistor. So let's say we have a 5-volt power source. So let's say here plus 5 volt. And we connect here to arbitrary rail up here. And let's connect this collector directly to the rail. And now let's think of what we do with the base and the emitter. So let's say here down here we have our ground. Let's call this ground. So that is then 0 volt. Let's write it out, 0 volt. And what would we do first? First, I think we do the natural thing. Let's connect a resistor to the base. And let's say this is, what is it? Let me think. Let us say this resistor is 10K. 10 kilo ohm. And then let's watch this scenario. You have plus 5 volt over a 10K resistor, then over the base emitter junction here, from base to emitter down to ground, where we end up having 0 volts, of course. So as you know, the base emitter path, it's a diode, so we lose 0.7 volts here. So we lose 0.7 volts here, from here to here. So then when we are here at 0 volt, then we are here at 0.7 volt. So if we're here at 0.7 volt, where are we here? Yeah, of course we are at 5 volt here. So the resistor sees over it 5 volt minus 0.7 volt. The resistor over the resistor are 4.3 volt. 4.3 volt over a 10K resistor. So we can calculate, okay, what current is flowing here through. Let's do the formula. U equals R times I, and we want the current. That means I equals U divided by R, and in our case that is 4.3 volts divided by 10 kilo ohm, and that is 0.43 milliampere. Okay, so not quite half a milliampere. Let's write this here down. Let's write 0.43 milliampere here. So we know what's happening at this resistor, 4.3 volt, 10K, 0.43 milliampere, all through this resistor. And of course, the current is all here the same. because it flows here through. And now comes the law of the transistor into play. Whatever current is flowing into the base, and that's a good thing to say and to remember, into the base, not out of the base, into the base, that is multiplied by a factor called beta. So the transistor has this factor beta, and that factor for the BC 547, for example, which I showed you earlier, it's about 200. So let's assume, yeah, sometimes beta is approximated with 100 because transistors are so different, and in this concrete case it would be 200. So let's go with the 200 for now. Beta is 200. And you can never rely on that beta, really. It really always is some kind of... And so what is said, hey, just take 100 and you're good, and that's a rough guess for you. But we'll take 200, like for the concrete BC 547 is the case. And so if we flow into the base this 0.43 milliamperes, then what is the collector current? Because the rule is whatever flows into the base, you multiply by beta and you get what flows into the collector. Okay, and let's calculate it. What is 0.43 times 200? And we're talking about milliamperes now. As of 0.43 milliamperes times 200 equals, and then is 43 milliampere, and then the double of that, because there's 2, that would be 86 milliampere. Okay, so we know now that 86 milliampere flow into the collector. So there's 86 milliampere, and that is the symbol I of collector, and that 0.43 is IB for I of base, into base. So out of I into base, we got by multiplying it by beta, the I into the current into the collector. And as you see, the current flowing into the collector is very much larger than the current flowing into the base. And if you sum up these two, you get what's flowing out down here. So we have this 86 milliampere, which comes from the collector. It has to go somewhere, this current. It goes out of the emitter. And this base current that flows in there, 0.43, it also has to go somewhere, and it goes also out of the emitter. Then we have 86.43 milliampere in sum, because these two currents join and leave the emitter here in the transistor. So that's really the cool thing we did. We said, okay, what do we have? What potential do we have right after the emitter? We have 0 volts here because it's directly connected to ground. And then we said, okay, what voltage do we have in front of the emitter at the base? 0.7 volt, because the diode here, the base emitter diode, it always drops around 0.7 volts, sometimes 0.6 something, 0.7 something, but 0.7 is a good rough guess. And then we said, okay, because we have 0.7 here and 5 here, we know what is flowing through this resistor, what kind of quantity of current, and then once we have that current flowing in here, then we can calculate everything else. Okay, now that is the first scenario. And oftentimes people think, and that's the trap here now, oftentimes people think, okay, no matter what I have as a situation with a transistor, I always calculate what current is flowing here, this path, and then I just multiply it by the factor beta to get the collector current like we just did, and then I know everything, so to say. But there's a slight thing to it, and I want to show you, because that's really I stumbled on to it, and I think it's really valuable for you too. Because the thing is, if we change this now, here we have the resistor at the base before the base emitter. Hi, cat. Now we put the resistor somewhere else. Now we put it down here and we see what changes and how we can explain that. So we again draw the transistor, but now we do not connect the resistor to the base. We just go straight up to 5 volts. We go from 5 volts to the collector. We go from 5 volts straight to the base without any resistor. And now we connect the emitter via resistor to ground to 0 volt. And you might think, okay, that's the same as, okay, we use again this 10K resistor here. And but it isn't. The thing is, you always have to watch what voltages you have coming from the 5 volts and going to ground. So we have here, we come from here, we have plus 5 volt here all the way, all the way, all the way, all the way. Okay, and now what do we have from here? We have from the base to the emitter, let's write emitter here, we have a diode and then we have a resistor. Okay, base emitter is a diode. That's cool. That's the reason, that's the thing to think about. Base emitter is like a diode. And then we know, okay, there must be, if that's a diode, there must be 0.7 volts here across it, yeah? From base to emitter, there must be lost 0.7 volts. So at the emitter, 0.7 volt lower. So, okay, where are we then at the emitter? Yeah, here. We must be, okay, we come from 5 volt, we lose 0.7, okay, we must be at 4.3 volt here. Okay, and then over the resistor. And then we are at 0 volt here. Okay, so over our resistor we have 4.3, then to 0. Okay, that's 4.3 volts over the resistor. Hey, wait, that's exactly the same situation as before. Okay. And then we say, okay, we calculated that already. That means there is a current here at 0.43 milliampere. Okay, 0.43 milliampere. And now the thing is, this 0.43 milliampere, it's not flowing into the base, as you see, but it is flowing, it is the current that is flowing through here. And the rule is, so you could think of, oh, okay, there are floating 0.43 milliampere through here, and then something else multiplied, and we'll end up with 86 milliampere here also, but that's not true. You have to, the base truth here is that you have always 5 volts here, and you'll always have 4.3 volt here. That's, you'll never end up with another situation where you always have 4.3 volts here. And because of that, we cannot have now a bigger 86 milliampere flowing through here, because if we would do that and there would be current flowing here, then the current would have to go through here, and we wouldn't have this 0.43 milliampere here. So the truth, just remember that. Watch what the diode is doing here, what the base emitter diode is doing. You have 5 volt here, then you have 4.3 volt here, no matter what. So you have, all in all, when the collector current, so I collector, and when the I base, when these two join, these two currents, they sum up to 0.43 milliampere. And then, and now is the cool thing, that now you know these two currents in sum, they are 0.43 milliampere. A very different situation from before. Before you had, okay, I flow 0.43 milliampere into the base, and then I get an additional multiplied current here because we had current flowing into the base, and then that summed up at the emitter. But now we're at a completely different situation. We know, and we have constant, because they have to be 4.3 volt here. We know what exactly must be the emitter current. And now the thing is that these two must sum up, I collector and I base, to the 0.43. And how they do this is by whatever flows in here, and it contributes to that, And what flows in here, it is beta times larger still, but still, if it's beta times larger, even though it just will be this, it won't get larger, but the ratio will be the same. And so we can think, okay, so I have with some current I beta is flowing in here, we don't know it, I write I beta, plus then some collector current that is flowing here, and these two join together, and they give this, they must be this current that is coming out of the emitter, this 0.43 milliampere. Okay, but the ratio must be the same, so I collector must still be beta times higher than I base, because that's the rule of the transistor. It multiplies the base current so that you get a bigger collector current. So must be I beta flows in plus, yeah, IC. Okay, but IC is just beta times IB, and that must be still the 0.43 milliampere. And if you make this easier, this equation here, then you get I beta, I base times, and you draw it out of the parentheses, then you are left with times 1 plus beta equals 0.43 milliamps. Now to get the base current, you simply do simple maths. You divide by 1 plus beta is 0.43 milliampere divided by 1 plus beta. And if we assume beta is 200, then we say I beta is equals 0.43 milliampere divided by 201. This is 1 plus 200. And what is that? It's 2.14 microampere. Okay. And the rest of it, so we have here 430 as the sum. We have 430 microampere, and you have around 2 microampere of base current flowing in here, so 2.14 microampere flowing in. So the rest to the 430 microampere flowing out here must be the collector current, and so this is around 427.86 microampere. So still the ratio fits, it's 2 here, and over 400 here, but they all sum up to the emitter current, and that's really the 2 configurations you have to remember. So let's draw them again. First configuration, resistor into the base and out of the emitter. So you calculate the current that's flowing in here, and then you multiply the current, and you know the collector current. That's the first scenario. And the second scenario is you have no resistor at the base, but you have the resistor at the emitter, and then you have to watch out that anytime you have to watch out that the diode drop is 0.7, and you'll get to what currents you have. So thanks for watching. I hope that helped. And with that, we are going to understand even more complex constellations with even more resistors added and stuff. So we'll see you in the next video. Please like and subscribe if that was somehow helpful to you. Thank you. Bye.